Hi everyone, this is Zhenguang Zhang from the University of Arizona. Today I'm talking about our paper, which proposes and implements a scheme that expands the role of preambles to support user-defined functionality in MIMO-based WLANs. This work is in collaboration with Dr. Hanif Raburi from Rochester Institute of Technology and my supervisor, Dr. Marwan Cruz. WLAN stands for Wireless Local Area Network, and Wi-Fi is a widely used WLANs. Based on IEEE 802.11 standards, Wi-Fi has evolved into its sixth generation with faster, denser, and more efficient connections. Are your demands all met? I'm afraid not, especially during this pandemic period when everyone has to stay at home. You may have suffered from an unstable signal when remotely meeting with your colleagues, while your father is watching videos on his tablet. Because both of you have the same traffic type, which are treated equally by the access point, considering access priority, then how could the AP coordinate channel access priority by other information in the packets? Well, there is another way to improve your connection quality by allocating more time or bandwidth resources. For example, the AP could wake up devices by negotiated schedule to alleviate contention. It also saves the battery life, especially for energy-constrained IoT devices. Wi-Fi 6 already has this feature. How could Wi-Fi 6 do it more efficiently? Besides coordination, you must have more security concerns. With existing upper-layer security measures, wireless devices such as surveillance cameras are easily compromised due to unprotected header fields. More importantly, the wireless channel itself is vulnerable to hijacking if message replayed, like the eye-opening crack. Furthermore, the eavesdropper could still sniff information from encrypted packets through traffic analysis. So failure desires authentication by AP's signature and privacy by encryption or modulation obfuscation. There are far more new coordination and security functions demanded in WLAN. Is it possible to support this coordination and security functionality by embedding information into certain field of Wi-Fi packets? Let's zoom in the packet to see where could we embed such information. The extra data from upper layer is concatenated after the preamble and header. The preamble is constituted of STF and LTF, which stand for short and non-trailing fields, respectively. Both of them are public node training sequences with repetitive structure for packet detection, synchronization, etc. Then the header indicates packet information. Especially seek field is standardized for predefined functions, and each function takes one specific field. For instance, the time to wake up field. In the future, with more emerging functions, more seek fields will be inserted in the rigorous frame structure, which extends the header duration. It also has to work with extra control frames. But we don't want to incur such communication overhead. Since recent 802.11 standards have similar preamble structure, our work focuses on popular .11 AC system operating on 40 MHz bandwidth. As we see here, Nexi preamble is preserved for backward compatibility, and extra VHT STF and VHT LTF are introduced for advanced technologies aiming at high throughput. The LTFs are also used for channel estimation, hence must be known at the receiver, where the functionality of STF doesn't require the knowledge of transmitted STF and receiver. Thus, we propose to embed user-defined bits within multiple STF swing form. It's called extensible preamble modulation and EP mode in abbreviation. By embedding bits in STF WinForm, EP mode is flexible to support frame-specific user-defined functionality. It does not need extra header fields or control frames that impact throughput. At the beginning of the frame, it will be decoded timely and quickly, and not corrupted by payload corruption or encryption. It's also backward compatible to work with existing protocols. Besides, it could be extended to all OFDM-based 802.11 standards, including MIMO systems. In this work, we assume the system model as the following. Say there is a 1-antenna client and a 2-antenna AP operating on 30 MHz channel bandwidth. The uplink is SIMO 1x2 transmission where the client embeds its priority into the STF or packet preamble. In turn, the downlink is MISO 2x1 transmission, and the AP embeds wake-up schedule for the client. However, our design should maintain four important properties of STF WinForm to support its critical functions for frame decoding. First of all, different antennas should have different cyclic shifts. Otherwise, signal from two transmitter antennas may end constructively or destructively. The received signal may stay low for a while due to such unintentional beamforming. Secondly, we have to keep the repetitive structure with standard duration and period for the purpose of reliable synchronization. Also, its dynamic range and peak to average power ratio should be as low as standard one. The former avoids AD conversion overflow underflow, while the latter accelerates signal strength regulation to obtain proper SNR for decoding. The last three entries could be realized by cyclic time shift and phase shift proposed by our previous work for a 20 MHz SISO system. Because these approaches don't change the periodicity, DR, and power of STF WinForm. However, to deal with challenges in MIMO, such as the first entry, they are generalized to be MIMO-aware and further combined with diversity gain techniques. The STF WinForm of S transmitter antenna is generated by SKs, the symbol on subcarriers, with subcarrier phase rotation gamma and spacing delta F. Then cyclically shift it by time t LCSI and normalize its power over NT transmit antennas. If we impose another cyclic time shift TCS, it creates a linear phase shift along SKs with slope mu equal to 2 pi 4 delta F TCS. In other words, if the initial phase difference of successive SKs are theta I, then the new phase difference would be theta I plus nu. For example, 8 different time shifts would be translated into 8 different nus and use 8 dpsk for modulating bits. So far, we could communicate a few bits by cyclically time shift. How could we embed more bits? Let's define such dependency among SKs as dependency pattern. Denote the dependency pattern for default .11ac STF and theta 0. The dependency pattern for our EP mode STF theta nu could be derived from theta 0. You may notice that theta 0 prime, the phase of S-14 is not specified yet. If we set it as delta phi, it will propagate to the phase of all following symbols, which is equivalent to shift the phase of STF WinForm by delta phi. For example, we could embed bits by 16 PSK for 16 possible delta phis. Beyond that, we take advantage of multiple antennas to obtain diversity gain and therefore improve the capacity and reliability of EP mode. In SIMO, we combine multiple received STFs for demodulation And in MISO, we apply anamorphic code to embed more bits. For instance, a cyclic shift of 0.1 microsecond corresponds to nu as a quarter pi and mapped to 0001 by 8 dpsk. Besides, we could map a phase shift of -7/8 pi by 16 psk to 001101. Let's now go over the combined scheme. The information bits are divided into two sequences. The Q sequence is mapped to an 8 dpsk symbol, which gives us a phase nu for the generation of pattern theta nu, while the M sequence is mapped to a 16 psk symbol, which is set as the first symbol as -14. Now, all Sk could be generated by S-14 with the dependency pattern theta nu. Finally, a novel STF waveform with an embedded bit sequence could be generated. In this way, any bit sequence could be embedded into the STF waveform by a general QDPSK and MPSK. These two approaches could also work independently. Then the receiver gets a package. It first goes through all STS, except the first one to detect their patterns, and finds the estimated nu whose corresponding pattern results in the minimum mean square error compared to received patterns. This estimated pattern is then used to construct the reference sequence of SK. Finally, the receiver calculates phase shifts of received SK from reference elements and sum over all STF symbols to account for noise. Moreover, the receiver with multiple antennas could obtain diversity gain by combining received STFs. EP mode with maximal ratio combining and equal gain combining are simulated under relay channel of 30 MHz bandwidth. Note that the BER here is the bit error rate of embedded bits. We could embed 10 bits in the LSTF with Q and M as 32, while matching the BER of BPSK payload. The capacity would be further increased to 20 bits per frame if we also embed in VHT STF. We also show the result of embedding only bicyclic time shift plotted in dash lines, where MRC outperforms EJC for demodulating Q sequence, whereas EJC performs better than MRC for M sequence. So they cooperate on preamble demodulation in SIMO. Similarly, in MISO system, to obtain diversity gain, we customize anamorphic code for EP mode. At first, using the basic scheme elaborated before, 2-bit sequences are modulated independently by 2 transmit antennas to get S1 case and S2 case for their own LSTFs. Then these 2 sequences are exchanged between 2 antennas with anamorphic coding and used to generate VHT STFs. The receiver has to execute anamorphic decoding before preamble demodulation. Our simulation shows that EP mode without anamorphic in SIMO is worse than SISO because it cannot decompose 2 interfering signals. However, EP mode with MISO anamorphic has around 4 dB gain over SISO and high SNR. Its capacity is limited to 18 bits per frame, even with Q and M as 32, because we couldn't select TCS randomly from 32 possible values. Instead, the sum of 2 cyclic time shifts should be different for each antenna to avoid unintentional beamforming. We did indoor experiments on a test bed where 2 USRPs separated by 2 meters serve as transmitter and receiver respectively. They operate on 2.5 GHz to avoid interference. and the bandwidth is downgraded to 400 kHz due to processing limitations of a host CPU, but is still equivalent to 40 MHz, as we have 128 subcarriers as the standard specified. Because of too low environmental noise flow, a synthetic Gaussian noise is added at the transmitter to lower the overall SNR. We embed 10 bits on each antenna by setting Q to 64 and M to 16, and evaluate the reliability of EP mode with MRC plus EGC in SIMO, and with alarmoting in MISO. It turned out that the BER of embedded bits is comparable or lower as BPSK payload in both cases. Thus, it reaches a capacity of 10 bits per frame for SIMO 1x2 and 20 bits per frame for MISO 2x1 system. We noticed that the BER of BPSK payload is not impacted by EP mode, an indication that the preamble function have been successfully maintained. More specifically, in MISO case, the accurate frame detection probability for EP mode with or without alarmity are both close to default preamble, which is around 80%. Also, as shown in the right figure, without any extra synchronization devices, the carrier frequency offset estimated by EP mode preamble is very close to that of the default preamble. In conclusion, EP mode embeds bits into STF waveform for user-defined functionality without impacting frame detection or decoding. Additionally, it's combined with diversity gain techniques to improve capacity and reliability. In our experiments, it achieves a capacity of 20 bits per frame with comparable BER as most robust BPSK payload in SIMO 1x2 and MISO 2x1 systems. We also propose the algorithms for its extension to higher bandwidth .11 systems. You may refer to our paper for details and numerical results. Our ongoing and future work focuses on the generalization of EP mode to higher order MIMO with customized multiplexing and diversity gain, as well as applications of EP mode on file security and coordination. Thanks for listening, and I'd like to answer questions online or offline.